said that this closeness property is with respect to some larger space. And then we've had that if we have a space group, in particular, we can write every element in that norm space as a sum of an element from a closed subspace and its orthogonal complement. Okay, so just to put everybody on the same page, it is still relevant to, even though this fact holds, it is still relevant to emphasize that we have to have a subspace that is closed, because there are various infinite dimensional subspaces that are not closed. And this is one of the examples. So we start with a space of continuous functions on -1, 1 segment that are real valued. We endow that space with a uniform norm. So since they are continuous on a closed segment, that means that they're also bounded. So this is always a finite number. Yeah? So now this is a nonlinear space. And within that space, there is a subspace of differentiable functions. All right? So why is that a subspace? Because when I multiply a differentiable function by a scalar, I get a differentiable function. When I add two differentiable functions, I get a differentiable function. So it's definitely a subspace. But it is not closed. And to show that it is not closed, the idea is just to construct a sequence of differentiable functions. So they lie in this subspace, but they converge uniformly in this norm space, to a non-differentiable function. Say you take a non-differentiable function, such as absolute value, and you construct this sequence. All of these functions are differentiable, so they are kind of like piecewise linear, and then they have quadratic component here, and you basically define it to make sure that derivative exists at every point. And then you make this quadratic component smaller and smaller, and you uniformly converge to a non-differentiable function. Therefore, this subspace is not closed. Okay? So that's one example, but you can say, well, that's not a Hilbert space. So is it the case that in a Hilbert space, every subspace is closed? And this is a counter example for that. Okay, so I have an infinite dimensional Hilbert space, and we know that every Hilbert space has an orthonormal basis. So I pick one orthonormal basis, say that, and then I want to consider this space, that is the span of U, which is defined to be the set of all finite linear combinations of elements of U. Right? So that is a subspace, because if I add two linear combinations, I get a linear combination and it's finite. If I multiply by a scalar, it's still a finite linear combination. But it is not closed, simply because not all elements in a Hilbert space can be represented as finite linear combinations. So some of them have to be infinite. So you just take one of those, an infinite linear combination. So every coefficient is strictly positive. And so that's just a condition which tells you that H lies in that Hilbert space. So that's just the L2 condition. So then if I just truncate that sum, these elements will lie in the span of U, and they will converge to that element, right? Which is not in the span of U. So again, you have an example where you have a subspace that's not closed. Okay. So recall that when we proved Risch theorem, we used exactly this fact. If I have a closed subspace, then its orthogonal complement contains a non-zero element. So that's how we've constructed. Using that non-zero element, we've constructed a representer. And in this example, you have a subspace that's not closed. And indeed, in this case, if you look at the orthogonal complement of that space, it is 0. And this is what it means to say that a certain subspace is dense in the original space. When its orthogonal complement is 0, or where its closure is actually the entire space. Okay. So those are examples. Now we can press on. So the story so far was that we've had a definition of a Hilbert space. So that was a complete space with a linear product. We've shown that for every Hilbert space, Risch theorem holds, which tells us that all linear and continuous functionals defined on a Hilbert space are representable by inner products. Okay? And then we've added more structure into our spaces. We've introduced the notion of a reproducing kernel Hilbert space, which will be a Hilbert space of functions for which evaluation functional is continuous. So therefore, by Riesz theorem, that evaluation functional is representable by an inner product. Inner product with some element. There exists such element for which I can represent evaluation as an inner product. And then I can just introduce the notion of a kernel simply through that element that represents evaluation. Yeah? And that's what we call reproducing kernel. Okay, so I know that evaluation at x can be represented by inner product, and I just call that element that represents evaluation at x, k.x. This will give me rise to kernel function. There is another notion of a kernel, which is just as an inner product between some features. So you start with some data, these x's and x primes, you transform them, images lie now in a Hilbert space, and I just take inner product between those. Right? So that's a notion of a kernel, and we've seen that reproducing kernel is always a kernel in this sense, because I can take a feature simply that maps x into this k.x, this representative of evaluation at x. Okay, and so that's the story so far. We're now going to press on and further discuss what do we mean when we say inner product between features, and then see the third notion of a kernel, and that's in terms of just positive definite functions. So all three will turn out to be equivalent by virtue of Moore-Aronson theorem, which we will, if there's time, sketch the proof of towards the end. Then we'll discuss another way to interpret reproducing kernel Hilbert spaces in terms of Mercer theorem. We'll have to introduce some additional notation and some additional objects there. In particular, these integral operators are interesting. Then we'll discuss a bit how do we get new kernels from old kernels by summing a bit kind of like we have a couple of kernels and we can construct the new kernels by taking sums and products of the old kernels. Okay. So let's review this definition of a kernel as an inner product of features. So I call the function a kernel if I can find some Hilbert space that's not necessarily an RHS and some map such that that kernel is an inner product. And I'll call that map a feature map, and I'll call that space a feature space. And we've seen that every RHS is a valid feature space because every reproducing kernel is a kernel. Okay, but this feature space representation of a kernel function is not necessarily unique. So what do I mean by that? So if I start with some function like that, so that's just an inner product between two vectors squared, I want to see whether I can represent that as an inner product in some other space. And indeed I can. If I could just expand this out, I get the following expression. And you see immediately I have three terms. They're all symmetric in x and y arguments. So I can break it up in the following way as an inner product between these three vectors. Yeah? So that's a kernel because it can be represented as an inner product between three vectors. But that representation is not unique because instead of taking the square root 2 x1, x2 here, I can just have 2 x1, x2 entries in the 4 vector. Right? So that's another feature space representation of the simple kernel function. So I can have two feature maps and two feature spaces. So very simple stuff. But one thing to notice is that these feature spaces are not reproducing kernel Hilbert spaces, because the way I've defined a reproducing kernel Hilbert space, it has to be a space of functions, and I have to be able to define evaluation on it. And there's no way in which I can define evaluation on three vectors or four vectors. Evaluation in terms of x. So I have to view the feature space as a space of functions on x, on my original domain. Okay. So that's just to state, well, this feature representation is not unique. Okay, so the third notion that we're going to introduce is a notion of a positive definite function. So I'll introduce a positive definite function as just some symmetric function with two arguments that satisfies this condition for every finite set of scalars A1 up to An, and every finite set of elements from X. So this quadratic form, in terms of A, is always non-negative. Okay? So that's standard definition of positive definiteness. And bear in mind, however, that this is how we call things in machine learning. We call this positive definite. In sort of more mainstream mathematics, this would be positive semi-definiteness. And positive definiteness would correspond to what we call strictly positive definite, which simply means that if I have mutually distinct points in the original space, the equality here, this being equal to 0, holds only when I just set all scalars to 0. Okay, so that's strictly positive definiteness, but we don't have to worry about that too much now. And so one can easily show that every inner product function is a positive definite function. And more generally, every kernel is a positive definite function. So this is a very easy proof. Maybe we can do that quickly. So let us assume that I have a kernel. So what does that mean? That means that I can represent that function as an inner product in some feature space. For some feature. I'm not saying anything about which it is. We know that it's not unique. Okay, and now I want to test positive definiteness of that function. Well, let me construct that quadratic form. For some scalars and some points in my original space. So by the property that this is a kernel, I know that I can write it in this way, so let us just do that. Every inner product is a linear function in both arguments, so I can take this sum of products with scalars ai and put it inside here, and this other sum and put it inside there. So now I just get an inner product of ai phi xi, a linear combination of the feature maps. Sum j goes from 1 to n, aj phi xj. But these two are the same thing, so they just differ in the index of summation. So this is just squared norm of this linear combination. And norm is always non-negative, so this is always non-negative. So therefore, every kernel is a positive definite function. That's just the proof. Okay, so we've shown every reproducing kernel is a kernel, every kernel is a positive definite function. So we just need to show that every positive definite function is a reproducing kernel to complete the loop. Yes? So that's what we're asking. We're asking that question. And this is the answer to it is given by the Moore-Arnstein theorem, which tells us that it is true. So every positive definite function is a reproducing kernel for some RKHS, and not only that, that RKHS is unique. So recall that we've had that the feature space representation is not unique. But if I restrict my attention to RKHS feature representation, that is unique. Okay. And so this theorem tells us that these three notions are exactly the same. And effectively what we also have done is we've established that the set of all positive definite functions, which actually has a geometry of convex cone, it's often studied, it's an object of interest in various areas of analysis, is actually, we've established a one-to-one map between that and the set of RKHSs in that sense in which we've defined it. So these are just some subspaces of the sets of functions, subspaces of which contain functions that are real valued and take arguments in X that have continuous evaluation. Okay. And when we get to this operations with kernels part of the lecture, we'll see that there is more structure to this bijection than just this. Somehow it preserves geometry in this space. Okay. So going back to this non-uniqueness of feature representation issue, we've seen that there are many feature space representations of a kernel, and we can work in one of them. So it could be convenient to think about kernels in that way. But we've also seen by Moore-Arnstein theorem that RKHS representation is unique. So how is that possible? So consider that example again. So we've had this representation in terms of 3 vectors. So let us now consider this expression as a function in y. Yeah? I know that there is also this representation for every kernel, because every kernel has an RKHS, and that's a valid feature space representation. And this, when I consider this thing, so this k subscript x is just k dot x, written in that way to emphasize that I'm thinking of this as a function of y. Yeah? So this is just k of x, y. And if I think about that as a function of y, so this can be expanded in terms of some simpler functions of y, i.e. y1 squared, y2 squared, y1, y2. And this feature space representation just gives me the coefficients in that expansion. Obviously, you can take things the other way around and consider this as a function of x, you'll get exactly another thing. But the point here is that even though those feature space representations are not unique, they are just expansions of the same function. And that function is unique. And that's just the kernel function, right? Okay. And so this is this other feature space representation. Again, just some expansion in terms of simpler functions. So different feature maps give coefficients of this function k dot x. Okay? And RKHS remains unique regardless of this representation. Okay, so we'll now talk about other way to interpret reproducing kernel spaces. And in particular, why do we say that functions that lie in RKHS are smooth in some sense? How is this in any way related to what we've discussed so far? Okay? So let us first introduce a notion of an integral operator. So far, we've basically made very few assumptions. We've just started with our domain being a non-empty set. Yeah? We haven't said anything about x apart from it being some non-empty set. And for k, we just require that it is a reproducing kernel or a kernel or positive definite function. These are all the same things. These very, very weak assumptions that we made on the objects of interest, right? So now we will introduce some further assumptions. We will assume that the space X is a compact metric space. So that you can think of effectively as just we're restricting our attention to X that's somehow similar to a segment on the real line. And the most important property that we will use from this assumption is that if I consider a continuous function on the domain X, it will be also bounded and uniformly continuous. Right? So that's the most important property that we will be using. So obviously it doesn't have to be just a segment. It can be any number of basically the segment raised to any power. So it could be an element of a high-dimensional space. It still has the same property that continuous functions are bounded and uniformly continuous. Okay? And having assumed that, we will assume that the kernel function itself is continuous, in addition to being positive definite. That will also imply that it's bounded and uniformly continuous. Okay. So what is integral operator? So I will start with now looking at a measure on X. You can think of it just as a probability measure. So X is now has sufficient structure. It is no longer just a set, compact metric space, such that I can define probabilities on it. Okay? And now I take L2 space with respect to that measure on X. And I define this map that sends L2 into the set of continuous functions on X. An assumption being that this is a compact metric space means that they are also bounded and uniformly continuous. Okay. I define this map in the following way. To every equivalence class in L2, remember that elements of L2 are not functions, they are equivalence classes of functions. So to every equivalence class F tilde, I associate a function defined in the following way. This being a function of X. Okay? So I take kernel, kxy, convolve somehow F with that kernel with respect to that measure, nu. Integrate y out, and I get a function of X. So here F, in this expression, is any function that lies in this equivalence class of L2 functions. Functions within the class differ at most on a set of new measure 0. And therefore, for every function like that, this integral is the same as a function of X. Okay?
Sorry, that notation. So F in F tilde, does mean they're both in L2?
So it means, so I'm kind of like trying to make the point that F tilde is not a function, but an equivalence class of functions.
Sorry, yes.
An element in L2. So that is an element in L2. But now that equivalence class itself is a set of functions. And I just pick any function from there. And that's a function which I can evaluate. I can say what f of y is. Right? F tilde of y doesn't make sense because it could be anything. It's just a single point. You know, and I can put any value in there. So as long as they differ at most on a set of new measure 0. Okay. So now I get a function of x that is associated to every L2 equivalence class. Right? And I take this this map and I compose it with inclusion of the continuous functions into L2. So what does this include? The set of continuous functions on X, we've said they're also bounded and uniformly continuous. Because they're bounded, they're definitely integral, right? They're definitely square root integral. So to every function in there, I can associate its class in L2 to which that function belongs. There is only one continuous function in there. There are many others that just differ on a set of measure 0. And I just do that. So I associate to that continuous function its class. So I go from L2, get a continuous function, and include that function again in L2. Right? So I get an operator. So I get an operator on L2 now. That goes from L2 to L2 by basically just doing this composition. Okay, so we've skipped effectively, we've somehow assumed something in here. We've somehow assumed that actually this mapping is well defined. This function is continuous. How do I know that? It's not obvious. So let's see that. Why that happens. Okay, so just to reiterate. So I defined this map, and I just wrote on the right hand side, I wrote something that is definitely a function of x. But how do I know that that's a continuous function? So I want to show that it's a continuous function. So let me just look at the difference of that evaluated at x minus the same thing evaluated at x prime. And I want to control the absolute value of that. So I want to show that if I make x and x prime sufficiently small, this becomes sufficiently small. Right? So I just write down the definition of these objects. They are both defined in terms of integrals. Integral is linear, so I can take things together. So what do I mean by that? I can write this as an integral kx y minus k x prime y f y d nu y. Do you agree? So that's just definition. So now, what is this object? So this is somehow just an L2 inner product between that and that. Do you agree? So that's just L2 inner product of two functions, just ax, bx, d nu x. And here I'm just treating these in terms of as functions of y, so I better write this way. And this has exactly that form. Okay? So now I get an inner product of this function of y. So I've now removed y as an argument. This is understood to be a function of the second argument, right? So I know that that's a continuous function because I'll assume that my kernel is a continuous function. So I can include that in L2. So that's now something in L2. And I can take inner product with that with something else in L2. And something else in L2 is F tilde. Okay? That's just now absolute value of an inner product. We can apply Cauchy-Schwarz inequality. So this will give us norm of F tilde L2 and the norm of this other object. But I'll just write that straight away because that's just the norm of that function in L2. So that's an integral kxy minus kx prime y all squared d nu y. Right? That is a continuous function on compact metric space. It is therefore bounded. Yeah? So this is definitely less than or equal to some constant, and in particular less than or equal to the maximum that that function takes. Right? So that's squared. So now that no longer depends on y, that's just a constant. I can take it outside of the integral. Yeah? So I just get some constant that doesn't depend on y. I take it out. I get integral d nu y. So if that was a probability measure, that's just one. Don't have to worry about that. But since we've kind of like we're considering general case, now nu is some measure, and I just have to multiply that by nu of x. Okay. So I also have, I've forgotten because I have a norm, not a squared norm. I have a square root over here. So when I take that square root, that gives me a square root of that. And that square and square root cancel out, and I just get an absolute value. Did that make sense? Okay, so that's what this whole thing is less than or equal to. And so let us just write down what we have so far. We have the square root of nu x and the norm of f tilde L2. And I have some max y in x, kxy minus kx prime y. But this is exactly what uniform continuity implies, that this object here can be made arbitrarily small when I put x close enough to x prime. Because that continuity delta does not depend on y. Yeah? So I can make this arbitrarily small. Therefore, I can make that arbitrarily small when I put x close enough to x prime, and this function is continuous. Okay. So this definition is well posed. Okay. So we have a way for every continuous kernel to associate to any L2 equivalence class a continuous function, which is kind of a neat thing because L2 functions are a much broader class of functions than continuous functions. We are somehow smoothing them down to towards the continuous class. Okay, so that's just that proof again. And so what do we have so far? We have this SK operator that sends L2 to the class of continuous functions. We have inclusion, and we have the integral operator, which is TK, which is an operator in L2. So it sends L2 to L2. Why is that useful? Okay, so this is just, again, making the same point that TK, even though it differs from SK only by this inclusion, and inclusion is just identity, right? They are still not the same objects, because images of SK are functions, so I can define evaluation of SK f tilde. I can talk about, this of X. But for TK, images are equivalence classes of functions, so I cannot do that. Evaluation is not defined in that space. So even though somehow they seem very similar, they are different objects, these two. Okay? And so now, why do we care about this TK? So we want to set the stage in order to, using this TK, interpret the kernel and its associated RKHS in a particular way. So we'll see now that these various properties of kernel function imply various properties of the integral operator. In particular, k being symmetric, which it always is, because it's a kernel function, implies that this operator is self-adjoint, which means it can swap places within an inner product. If it is the property of kernel being positive definite implies that this operator is what is called a positive operator. And when k is continuous, this operator is compact. Don't have to worry about that too much, what the definition of compactness means. Let us just say that why do we care about this? We want to set the stage in order to apply a deep result from functional analysis, which is basically just a generalization of eigendecomposition to infinite dimensional spaces. So this is called spectral theory. What does it say? Well, it exactly applies in this context when we're considering compact self-adjoint operators. Then spectral theory implies for every such operator that I can diagonalize its action in particular way. Meaning that I can find an orthonormal set within that Hilbert space and a set of scalars which decrease monotonically and converge to 0, such that action of T on every element of F is the same as projecting that F to each element of the orthonormal set and then just scaling it in that direction. So this is just like eigendecomposition of a matrix. We want to generalize that. It's not true for all operators, but for these compact self-adjoint operators, you get exactly the same thing. And in particular, because the operator is positive, that's just like matrix being positive definite, all these eigenvalues are also positive numbers. Right. And the operator being self-adjoint is used similarly as a result that symmetric matrices have real eigenvalues. Yeah, so that's why we need that assumption. So that's spectral theorem.
Yeah,
and
how many of those eigenvalues are there? Is it most countable?
At most countable, yes. That's a so there could be an infinity of them, right? But a countable infinity.
Okay, but they also can be finite.
It can be. So then they are a finite set in the case when the operator is a finite rank operator. Mm-hmm. So that's exactly the number of non-zero eigenvalues is exactly the rank of the operator. Okay. So, and you get this at most countable because the operator is compact. Otherwise, you cannot actually expand this in terms of a countable basis. But obviously, if a Hilbert space is separable, then it has to be a countable orthonormal set. Okay, so this sets the stage very nicely to for talking about Mercer's theorem. So let's just review what we've had so far. We've assumed that X is a compact vector space. We had some continuous kernel, and we've talked about these integral operators with respect to some measure nu. So let us now just make assumption that this measure is such that it is supported on the whole space. This is not a very strict assumption, right? And then we know, as we've seen on the previous slide, that we can conclude various things about this operator. It's compact, positive, self-adjoint, so we can apply a spectral theorem to it. So there exists some orthonormal set in L2. So notice I put tilde in there. These are not functions, they are equivalence classes. Yeah? And eigenvalues lambda j, they are strictly positive. This index set is at most countable. I just said that, so E tilde j is an equivalence class. It's an element of L2. And to every such E tilde j, I can associate a corresponding continuous function, Ej, in the following way. Okay, so let's see why that is the case. Okay. So I said that I have E tilde j, that's in L2, and I define Ej in the following way. Lambda g j minus 1, sk E tilde j. Right? So that's definitely a continuous function because I know that sk applied to any L2 is a continuous function, and I just multiply with the scalar. So this is definitely in Cx. And I'm also claiming that this is exactly the continuous function that lies in this class E tilde j. So far I've just said it's a continuous function, but I'm just now saying that it is actually picking from this orthonormal set an element that is a continuous function. So how do I know that? Well, Ik is E tilde j. No. I'm considering this object Ik, inclusion of Ej. So what is Ej? Ej is this thing. Right? Take the scalar outside, and I get exactly this composition of Ik and Sk applied to E tilde j. This is Tk applied to E tilde j. And when I apply Tk to E tilde j, I know that E tilde j is an eigenvalue of Tk, right? Because that's how I've obtained these scalars. So this is exactly lambda j minus 1, lambda j, E tilde j. So it's just E tilde j. So the class of the continuous function Ej is exactly E tilde j. Okay, and then I get Mercer's theorem. It tells me that under all these assumptions, and when I'm define Ej in the following way, I get that the kernel can be written in the following form. It is exactly expanded in terms of evaluations of bunch of continuous functions, Ej, that arise from the orthonormal basis in L2. So it happens so that if I start with a kernel function, it satisfies all those assumptions, I can write it in this form. Okay, and we'll see why that is useful. So what does this give us? First of all, it gives us another feature space representation. So I've written that kxy is this sum, but that's just a sum in the inner product in the small L2 of two sequences. One of them is square root lambda j, ej evaluated at x. The other one is square root lambda j, ej evaluated at y. So that's just free by noticing that this is exactly that, equal to that. But this is exactly writing the kernel function as an inner product in some Hilbert space. And in this case, it happens that this Hilbert space is small L2. And these are the feature space representations. And so this is just another feature map, right? It's called the Mercer feature map. You start from data, you send that to some sequence. And that sequence is particularly just evaluating your data point at a bunch of continuous functions and scaling appropriately. So you get, instead of that abstract feature map k.x, you get a very nice interpretation of what's going on. You're just evaluating a bunch of functions at x. And so how do I know that this is in L2, in small L2, this sequence? How do I know that this feature map is well defined, in other words? Well, it's definitely square summable, because if I just take sum of the squares of that sequence, I'll just get lambda j ej of x, ej of x, right? Which is just k of xx. So that's always finite, because k is just a function, so that cannot be infinite. Okay, so that map is well defined, and there we go, we get another feature space representation. Okay, so this will lead us, what we're going to do now, it will lead us now into an interpretation of what actually functions in RKHS are. So far we've just seen that the kernel function has an interpretation as an inner product in small L2 using these ej's, lambda j's. So now I'm going to say, well, every function in the RKHS also has interpretation in terms of ej's. Okay. So first, let us notice this simple result, that if I just now take a bunch of scalars here, let's be precise about this. Right? So I'm going to take my functions that I care about. These are the functions from the kernel expansion. And I'll just take some linear combination of them. And I take these coefficients in a very special way. I take them so that aj divided by square root lambda j, this sequence is in small L2. That's square summable. So this is much stronger restriction than saying that aj themselves are square summable. Because remember that lambda j are some scalars that go to 0. Right? So for this sequence to converge, right? With this going to 0, this has to drop to 0 even faster. So it's much stronger than saying that sum of aj squared is less than infinity. So that's how I pick my coefficients. And now I'm claiming that this actually converges absolutely for every x, just this series. And this is again yet another application of Cauchy Schwarz inequality. So what I'm going to do, I'm going to take the absolute value of that, divide by square root of lambda j, and multiply by square root of lambda j. and then apply Cauchy Schwarz, or if you want to think about it in that way, just Helder's inequality. And basically, now this inner product will be less than or equal to L2 norms of these sequences, these two, this one and this one. And we've assumed that this one is square summable by construction, and the other one actually again just boils down to evaluation of a kernel function. Okay. So that implies that this thing is just some function of x, right? It's not going to blow up to infinity. Whenever I pick coefficients in that way, it's not going to blow up to infinity. It will just be some well-defined function on the domain. So you see where this is going. We're going to now show that exactly that it is exactly the RKHS function, and that's this theorem that characterizes Mercer representation of the reducing kernel space. Again, restate our assumptions. X is a compact vector space. K is continuous kernel. And I define a space of functions in this way. I take functions exactly to be in that form that we've seen on the previous slide. I take my AJs and I pick coefficients that decay appropriately, right rate. I endow this space, which is just a space of functions so far, with this inner product. I say that if I have a function in this form and function in that form, I will say that its inner product is defined in this way. Yeah. Then this will exactly be the RKHS of K. So this theorem exactly tells us what the RKHS functions of K are. They are all functions that can be written in this form, such that these coefficients decay at the right way, in the right way. And notice one thing. We've now shown that this is the RKHS of the kernel. This depends obviously on the underlying measure, right? When we've defined this space, lambda j's and ej's, they are eigenvalues of an integral operator with respect to some measure. But what we get at the end, this RKHS, is unique for a kernel, so it doesn't depend on the measure. Right? So I will just get a bunch of functions in this way. They will be expanded in some orthonormal basis EJ, all right? And that basis depends on the underlying measure, but the function that I get at the end does not depend on the underlying measure. So that's a very, very powerful result. Okay. So let us try to show this theorem. Okay, so we just start with some space. We say that claim that this is an inner product. We have to first show that this is actually an inner product that is first of all an inner product space, then that it's a Hilbert space, and then it is a reproducing kernel Hilbert space. So you can easily see that this satisfies all the properties of an inner product, which is linearity and symmetry. Apart from the positive definiteness, which is maybe not clear immediately. So what I want is that this is equal to 0 if and only if the function in here is 0. So what am I saying? I'm saying that if I take some function f, that's in this form, some aj, ej, and I want to take an inner product of that function with itself, yeah? This has to be always strictly greater than 0. So this is just some aj, ej, some aj, ej. Definition of an inner product. Some aj times aj squared divided by lambda j. Definitely strictly greater than 0. as long as one of the coefficients is not 0. Yeah? And so you only get that being equal to 0 when all of the coefficients are 0, when our function is 0. So that's a valid inner product. That's the first thing we need to prove. Now we have to show that this is actually a Hilbert space. How do we know that it's even a Hilbert space? Well, this is maybe slightly tedious to show. So what we have to show is that it is a complete space. So we have to show that every Cauchy sequence is convergent. So I pick a Cauchy sequence here. All of these functions are in this form. So I just vary coefficients. And right there. So what does this Cauchy condition mean? That means that this can be made arbitrarily small when n and m are beyond a certain level. Yeah? But what is that? By definition, when you plug in the definition of fn and fm there, you get just that. Yeah? So that's now something in terms of these sequences. And this is nothing else than actually a difference in terms of small L2 norm of certain sequences. Right. So what we get with that is that this sequence in N of elements in small L2 is definitely a Cauchy sequence. I've somehow established isometry between these Fs and these sequences. So I get that with a Cauchy sequence of 1, in one space, I get Cauchy sequence in another space, but we know that that's a Hilbert space. So there must exist something this converges to. And then we just go back and say, well, then there must be a limit in the original space. Okay, so not too crucial, I guess, part of the proof, but just bear in mind that we've established that H is a Hilbert space by simply establishing some connection to small L2, which is definitely a Hilbert space. Okay, so that shows that the space we've defined is a Hilbert space. So now we need to show that it's an RHS. So there are two conditions for a space to be an RHS, if we think of it in terms of reproducing kernels. First one is that this k dot x function has to lie in that space. So let us check that. Does it lie in that space? When? Well, by Mercer's theorem, I can just Mercer's theorem tells me that kx prime x is just some lambda j ej x prime ej x. So now if I want to consider this as a function of this first argument, I just put the dot there, and this thing I can remove, right? So I get ej of x, and those are now scalars, and I just get ej. So there should be an x prime there, but we put that dot there. Okay. So now that's exactly in the expansion that we want it to be, expansion of ej functions with some coefficients, and only thing I need to show is that these coefficients decay at the right rate. Okay, and so to do that, I just have to show that this sequence of coefficients, so this is aj, I have to show that the sequence of aj divided by square root of lambda j is in L2, which is just here lambda j ejx divided by square root of lambda j. That's what I have to show. Yeah? So let's show that. Sum of squares of that. That cancels out with that square root. I get the square root, then I square it again. So I just get sum lambda j ejx squared, which is just ejx again. That's again just kxx. Again, something finite. So we know that k dot x lies in the space that we've defined. And we're already halfway there. We just now have to show that k dot x is this representative of evaluation, that it also has the reproducing property. So let's do that. Write NEF. NEF is in this form. K dot x, we've seen what it is. It's in this form. And so I just have, again, this expansion in terms of EJs for some coefficients. I apply the definition of an inner product. I get AJ times these coefficients, lambda j, EJX. Lambda j and lambda j cancel out. And I just get my function f, evaluated in x. So certainly, this is an RKHS that corresponds to k, because k dot x is in H, and k dot x has a reproducing property on that space. But since we know that RKHS is unique by Moore-Outside theorem, this space of functions actually does not depend on the underlying measure mu. So it doesn't depend on a particular choice of these EJs. So why does this imply in any way that the functions in RKHS are smooth? So let's consider an example. If you have something like a Gaussian kernel, and pick a particular measure nu, compute the eigenvalues and eigenvectors with respect to that underlying measure. So there could be something like this. These continuous functions that correspond to that kernel are expressed in terms of these Hermite polynomials. Doesn't matter, just some continuous functions. And lambdas decay at a particular rate. So let's plot a couple of these first functions, first EJs. So the first one looks like that. Has one bump. The second one has two bumps. Third one has three bumps, and so on. So they somehow have, they are becoming rougher as I increase index j, right? And I also know that this lambda j sequence decays. So this somehow implies that this norm of f regulates smoothness of a function, right? In particular, if I just have a constraint that f is in RKHS, then this is the constraint I'm looking for. That when I apply the definition of a norm for that f, I should get something that's finite, because if it's infinite, it's not in the space, right? So if I just expand this out, this is just inner product of f with itself. It will just be in this form. We've seen that already. And this has to converge, this sequence. And again, lambda j goes to 0. Therefore, this aj has to go to 0 as well. So the coefficients have to decay very rapidly for this function to be in the RKHS. And exactly the coefficients further down the line are terms that correspond to these rougher functions. Okay, so that's why the norm of RKHS norm regulates smoothness. Okay. Okay, so I'll just now briefly go through an interesting relationship we can establish using this machinery that we've just built between the RKHS and the L2 that we've started with. So when we've set a measure nu and introduce an integral operator with respect to that measure, we've got some set like this, some tildes, E tildes. And so that's just an orthonormal basis in a Hilbert space. So I can just, for every element in F, in L2, which are called F, if I wanted to be consistent, I should have put F tilde there, but it doesn't. So for every F in L2, I project that to an element in the orthonormal basis. So these are like Fourier coefficients, if that was a Fourier basis, yeah? So I just rewrite what I had by spectral theorem, that the action of this dk is just projecting to a basis and then scaling up in that base in that direction. Right? So I also can associate to that setup an operator of which this operator is a square in a sense that you apply it twice. Yeah? So that's just scaling in the respective directions by square root of the eigenvalue. So when I apply that twice, I get that, right? Apply by the square root, apply by square root. Okay? So, and then I know that this is my RKHS. It's in this form. So what this tells us is that when I just look at the L2 norm of f, this is just equal to the sum of the squared Fourier coefficients. That implies that my Fourier coefficients are in small L2, right? But since the Fourier coefficients are in small L2, the sequence defined in this way, square root lambda j times those Fourier coefficients, satisfies this property. Okay, so that means that this function is in HK. So just started with any function f in L2, expanded it in an orthonormal basis, got those coefficients, and then scale those coefficients with the square root of lambda j. I got a function in the RKHS. Okay, so what have we done? We've established a one-to-one map between functions in L2, sequences in small L2, and functions in the RKHS. Right, and it's not only a one-to-one map, it also preserves inner product. L2 inner product between f and g is the same as small L2 inner product between Fourier coefficients. You all know that. But it's also the same thing as this inner product between RKHS functions. Because what is an inner product between these RKHS functions? I'll take multiples of these coefficients and I'll divide everything by lambda j. So that's the same thing as this. So I just get sum of the product of the Fourier coefficients. So actually this operator tk a half, what it does is somehow inducing some kind of like isomorphism between a part of L2. So I didn't say that this is a basis, it could be kind of like a smaller, simply smaller set. So a span of that set and the RKHS. So you can also view RKHS in that way, just some space that is somehow isometrically isomorphic. It is for all practical purposes the same as some subspace of L2. And again, reiterating that we had that relationship, and recall that what this does for the function k.x, it just expands it in this way, and that's just the Mercer's theorem. So we've had that this is a canonical map. We've had that these coefficients are the Mercer's map. So again, you get this non-uniqueness of feature space phenomenon that we've observed. That these Mercer feature maps are just some coefficients of the canonical feature map of the function k.x, just like before. But now they are coefficients in terms of an orthonormal basis, so they are somehow a smarter way to expand my function k.x. Okay, so that concludes Mercer representation of RKHS, which gives us intuition of why we are considering these functions in RKHS as smooth. So we'll just briefly now discuss how I can construct new kernels from old kernels. So this should be fairly straightforward. So I'll just review a couple of facts. Say I have some kernels k, k1, k2, kernels on x. I take a scalar that's non-negative. Then alpha k and k1 plus k2 will also be kernels. So this is what I meant when I said that a set of all positive definite functions, which are the same thing as kernels, is a convex cone. That means we can add things together, we'll stay in that space, and we can multiply, but not with any scalar, only with a non-negative scalar. Difference of kernels is not necessarily a kernel. This is just like saying, well, you cannot multiply with something negative, right, and then add them together. Simply because I have to have a kernel being representable as an inner product between feature space. So this kxx thing is some kind of norm. And if I want to construct a kernel as a difference between two kernels, it is possible that I will get something if k2xx is for some x smaller than k1xx. I will get something negative. I cannot have that. So in general, a difference of kernels is not a kernel. So this is what I've said. So this means that the set of all kernels is somehow a convex cone. And when I add kernels together, what kind of RKHS do I get? So they are still kernels, so there is some RKHS that corresponds to them. So it turns out very nicely that actually the RKHS of the sum of two kernels is just set of some functions that can be represented as sums of the original functions in the original RKHS. So say you add two kernels together, one is Gaussian, one is Laplacian. Yeah? So the kernel that you get will constitute of RKHS functions, which are sums of Gaussian bumps and Laplacian bumps. That kind of makes sense. Okay. Perhaps more interestingly, we can also multiply kernels together. So if I have now two domains, x and y, and one is k1 is kernel on x, k2 is kernel on y, I can construct this new kernel simply by saying when you get a pair of x and y and another pair of x and y, you compute the kernel between those two pairs by simply multiplying together kernels between x's and kernels between y's. So say x is an image, y is a label. So you have a smart way to construct a kernel on images, smart way to construct a kernel of labels. Why do you need to get a kernel on image label pairs? You just multiply them together. Obviously, those are not the only kernels you can consider on the product space, but they are sufficient for many applications. And in particular, if I just have these being in the same space, then I get again a kernel on the original space x. I can also consider it to be a kernel on the x squared, but I can also consider it to be a kernel on x, and given in the following way. So if I multiply, say, a Gaussian kernel with a Laplacian kernel, I'll also get a kernel in its own right, and it has some RKHS. And what is that RKHS? Well, it turns out that that RKHS of a product kernel is, in some sense, exactly the same as taking a tensor product between individual RKHSs. So that doesn't mean anything particularly deep. It just says that if I have this f in the hk1, hk2, right? This means that I can write f as some sum of product of functions f1 of x and f2 of y, where f1 is in hk1, f2 is in hk2. So that's somehow the simplest thing that you can consider on the product space. You just multiply all the functions in the original RKHSs together and sum them up. Okay, so that's what I meant when I said that this bijection that we're constructing by Moore-Arnstein theorem between kernels and RKHSs has some structure with it. We have that the sum of things in here corresponds somehow to the sum of things in there, product of things in there corresponds to the product of things in there, and multiplication is scalar as well. So this convex cone, these two convex cones have exactly the same geometric structure. Okay, so we've seen that we can add kernels together and multiply them together. We can use this fact to construct interesting new kernels. So let's just start with a trivial linear kernel of Euclidean space. Kernel is just a linear product of features. Data points themselves are some features of themselves, so that's a kernel. Okay, we know we can multiply it with itself and add it to other kernels. So if I just take a polynomial that has all coefficients non-negative and put this inner product through that polynomial, that will be that thing to some power plus that thing to some other power times some non-negative scalars. So I get at the end the kernel. This is, for example, how you would get a polynomial kernel. That's exactly that form. Because when you have a plus there and you expand this using a binomial theorem, you get all coefficients non-negative. Yeah? And also it turns out that you can continue this reasoning and make this sum have infinitely many terms, subject to some convergence conditions. So whenever you have a function that has no negative, that has a Taylor expansion with no negative coefficients everywhere, passing an inner product through that function will give you a kernel. Okay, an example of that obviously is an exponential function that has all Taylor coefficients positive. Yeah. So that's why this is a valid kernel. So just outline some of the kernels that are useful, and we can also from here derive Gaussian kernel. So let us first start with one very simple kernel. You start with your original domain is R to the D. You define a feature map in the following way. It goes from R to D to R. Define a feature just in this way. It is just some function of x. Right. So that's just a valid feature map. I haven't said anything yet. Okay, so now I can define a kernel K tilde as an inner product in R, which is just a product of those features. So that is a kernel. It's not a very good kernel, but it's a kernel. And I also have an exponential kernel, and I can multiply it with that kernel that I just constructed. And once you do the math, multiply these two together, you get exactly the Gaussian kernel. So if you want, you can now basically unroll the whole thing. We have said what the sum of the kernels imply for the corresponding RKHS in terms of the individual RKHSs. We said what it also implies for the products, and we've constructed a bunch of kernels by taking sums and products successively. At the end, we've got the Gaussian kernel, so you can unravel the whole thing and interpret the RKHS of a Gaussian kernel in that way. Okay, so we have about 10 minutes to sketch this important theorem. So the proof in the notes is very detailed because I'm not going to get far with this. Any questions at this point? Comments, questions, anything?
This relation between the Hilbert space and the L2 in 2.
Mm-hmm.
Can you say some more about that? Where this is actually useful for problem? you know you have this relationship, but
Yes.
where would I
Yes.
use it?
So, well, let's just say it's another interpretation of an RKHS, right? So you established exactly isometric isomorphism between the RKHS and some subspace of L2. So in many ways, this tells you interesting properties of your RKHS. For example, how big it is. Often when you're doing hypothesis testing with kernels, you're interested in properties which basically tell you how rich your class of kernel functions is. And one of the useful properties is for that class of kernel functions to be, say, dense in all L2 functions. And you can exactly get that result using this correspondence. And being dense in L2 functions basically means that every L2 function can be approximated to an arbitrary small fidelity with an RKHS function. So even though they are smooth, RKHS functions are rich enough to capture all interesting functions that you may consider for the problem. Any other questions or comments?
Can I ask how actually do you define inclusion? Like how precisely do you define inclusion?
How do I precisely define an inclusion in this context? So let's go.
Unless it was somewhere and I've missed it.
So you agree with that all continuous functions have a class in L2 that includes that continuous function, because all continuous functions are bounded on this domain, therefore they can be integrated. So inclusion is just defined by associating to every continuous function like that its corresponding class. Having said that, there is also there's another interesting interpretation of inclusion in this context, that it will be somehow an adjoint of SK. But maybe that's a bit too technical. So it's just that. So it's just like if you thought of this as a space of functions with some representatives, right? So it's an equivalent. It's a space of equivalence classes of functions, but within that equivalence class you have functions. Mm-hmm. And say you pick a representer. If there is a continuous representer of that class, let's pick that. Mm-hmm. Some may not be continuous. And so all continuous functions will have their corresponding class in there. And I just associate to that continuous function its class. And they will all have different classes as well, because you cannot have two continuous functions that differ on a set of measure 0.
Okay, I get the kind of interpretation, but it would still be interesting to see how you actually write it down. Or where can I find it?
So Steinwart and Crispin book goes in some detail on these issues, and especially discussing how inclusion is actually an adjoint of this SK operator. So in some sense, TK is SK star SK. And that's exactly why it's a positive operator, right?
So can you define it in this way as an operator of SK?
You can define it that way, sure. And then you have to show that it exactly corresponds to this sort of inclusion identity kind of operator.
So it's section 4.5 is
4.5, yes. Okay, so let's just spend now 5 minutes. Just if you're interested in the proof, I encourage you to go through it in detail in the notes, because it's actually described in entirety in the notes. I'll just outline what are the steps, main steps. So what Moore-Einstein theorem wants to do, it wants to start with a positive definite function and show that there is an RKHS. So you have to construct a space of functions for which that positive definite function is a reproducing kernel. Huh? So first, what the proof proceeds in the following way. First, you have to construct sort of a space that may not even be a Hilbert space, and that is called in the nodes, and the proof in the nodes is based on this Berliner and Thomas Mann book, pre-RKHS. So this is just a space of functions that has an inner product, need not be a Hilbert space. And then you have to show for that space these two properties. First of all, the evaluation functionals are continuous on that space. So that's something that we want to, from the RKHS as well. But we first have to show it on a simpler space. And the second property that requires somewhat more technical, it is a certain property that every Cauchy sequence in the space that we construct has to satisfy. So whenever it converges pointwise to 0, it will also converge in that norm that we endow the space with to 0. So this is pre-RKHS. This is a valid pre-RKHS. You just take a span, which is we've seen, like on the example of non-closed spaces, just a set of finite linear combinations of functions from here. So all the functions are in the following form. Just sums of Gaussian bumps if you have a Gaussian kernel. You consider that space of functions. That's not even a Hilbert space yet. It's not even an inner product yet, because we haven't defined inner product, and you define inner product in this way. The usual way that you see many times already. But now we're just starting with a positive definite function and building the space. We say, let's consider the set of all linear combinations, and let's endow it with inner product in that. So the first step in proving the Moore-Arnold theorem is that this is a valid pre-RKHS space. It satisfies those two properties that we defined. And the second step is now saying that whenever you have a pre-RKHS space that satisfies those two properties, you can build from it an RKHS. So this kind of like modular proof of the theorem is useful because it precisely gives you the conditions under which you can build an RKHS from some underlying space. Right. And this, in statement of theorem, I've underlined how to build that space. So you just set, given H node, you set H to be the set of functions for which I can find a Cauchy sequence in the pre-RKHS that converges pointwise to F. So you take pre-RKHS and you add to it pointwise limits of all Cauchy sequences. This will be an RKHS. So I think I'm gonna stop there. So that just outlines furthermore the steps in this proof. Again, it's all in the notes, and that's just restating what we've had. That these three notions are all the same, which is precisely given by the virtue of this Moore-Arnold theorem, which completes this cycle from here. These two directions are trivial, but that is highly non-trivial. So what that tells us is that as long as you have a positive definite function, there is a corresponding RKHS, so you can do any learning algorithm with that positive definite function. So it gives justification for kernel methods. And that's it. Thank you.
Okay, thanks.
Any other questions or comments?
I need more coffee. Is my new coffee, sorry.
Well, it's really technical, but we wanted on purpose to make this and last part of lecture, I guess, focus on the underlying theory. So you get kind of like a bit of both worlds.